Okay, good afternoon and welcome back. Just a reminder, I'm Bill Betton and I'm your host for this afternoon session. We're moving on to our second talk here, and that is going to cover a very, very interesting project. It's the Coventor emergency ventilator alternative, and it's going to be lessons learned from the early stage development of the first FDA emergency approved ventilator alternative for COVID-19. May also be the longest title that we've had on any of these sessions as well. And unfortunately, Art Erdman was not able to join us today, but with us we have his partners in crime on this, Dr. Stephen Richardson, who's a cardiac anesthesiologist from mHealth Fairview, and he focuses on primarily patients undergoing cardiac surgery, heart transplantation, lung transplantation, and cardiac device implantation. And he actually was responsible for leading the development of this first FDA emergency use case for the ventilator. And with him is Aaron Tucker, who's a PhD student in mechanical engineering at the University of Minnesota's Earlbach Medical Devices Center. And his specialty and focus is on early stage medical development, machine learning, and blood glucose forecasting. And he led the early stage development for the Coventor. So I'll invite them to come up here, and they've got an interesting presentation for you. Hold your questions till the end. I'll have a microphone and bring it around, and feel free to ask questions at that time. Gentlemen, please join me in welcoming them.
All right. So I hope everybody's enjoying themselves. It's great to be back in person. So as Bill mentioned, I was the lead engineer on the early stage development of the first FDA emergency approved ventilator alternative for COVID-19. So today we're going to talk about some of the major lessons that we learned from producing 3,000 emergency ventilator alternatives in 67 days. And we hope that through this unique process, we learned a thing or two that we can pass on to you guys. So just quickly go over the agenda. Bill already introduced us, but I'll quickly talk about our roles within the project, give you an introduction as to what the Earlbach Medical Devices Center is. Most people are not aware of our unique standing in the university. Then I'll have Steve talk about the background for this and the motivation for why we underwent this project. We'll give you a brief overview of the actual timeline and how we went about this, and then we'll get into the lessons learned as well. So, as Bill mentioned, Art couldn't be with us today. He's unfortunately sick, but he was responsible throughout this project for managing the personnel and resources that the university committed to this. So he was really instrumental in making sure that when resources needed to be moved and resources needed to be acquired, that we had what we need. And then Dr. Richardson, Steve with me here, was actually the lead clinical lead on this project. And like I said, Steve also was the primary motivation. He came up with the idea in the first place, so we have him all to thank for this. And then myself, I was the technical lead for the early stage development of this, and I am a PhD student in mechanical engineering, and I will be hopefully graduating soon. So first, get into the Earlbach Medical Devices Center. So what is the MDC? So I'll refer to the Medical Devices Center as the MDC throughout the rest of this presentation. So we are an interdisciplinary center at the University of Minnesota, which combines basic research with translational research, education, and training. So we are currently in the University Medical School in the Institute for Engineering and Medicine. So we started in 2008, but really the story starts in 2001. So Dr. Erdman had a vision for an academic and research-minded medical device conference, and he answered a call from the university president to start a new conference in 2001, known as Design of Medical Devices Conference. So this is an immediate success, but Dr. Erdman quickly realized that despite having the strong medical device ecosystem in Minnesota, there is no medical device focused center at the University of Minnesota. So After several years of success of the Design of Medical Devices Conference, the MDC was founded in 2008. So what do we do at the MDC? I'll briefly go over 5 focus areas. So we host the Design of Medical Device Conferences. We have 2 training programs, one for people with advanced degrees and one for students in their first or second year of undergraduate education. And both of these are immersive innovation learning and innovation-focused programs where we take our trainees through the ins and outs of developing a medical device, from the early stage through some of the unique aspects of the medical device market. So that covers 3 of our programs. We also maintain extensive prototyping facilities, a lab space with design software, top-of-the-line 3D printing, anatomical segmentation. And then we also maintain collaborations, both inside and outside the university, with companies large and small, groups large and small, in academia and outside. So, last thing I'll talk about briefly with the MDC is our important relationship with the University of Minnesota. So, I already mentioned that we are a member of the Institute for Engineering and Medicine, which is an interdisciplinary research center committed to building relationships between the clinical side and the engineering side. And as a result, we've had the benefit of working very closely with many physicians across the mHealth Fairview network. So I think we're at over 100 unique connections that we have. So that's something that we're really proud of and something that we look to cultivate at the MDC. So we've also, like I said, had the pleasure of working with many companies, large and small, over the years. So one of the things that we focus on is innovation and how do we teach and practice it. So we believe that everything starts with a needs statement, and we truly try to hammer this into our trainees, whether it's our fellows or our undergrads or our engineering service workers. And as you know, medical device market has unique stakeholders such as the FDA, and we really focus on teaching and practicing ideation within that framework. One of the other main focuses that I already mentioned, that we maintain extensive prototyping facilities. So rapid prototyping with high quality testing is one of our core functions, and something that I hope you'll see throughout this presentation as an important area of success when going through this development process. And then finally, we really preach on involving stakeholders such as physicians and other healthcare workers and the FDA as early as possible in our implementation phase. So over the years, we've trained over 200 undergraduate interns and over 80 fellows, so people with more advanced degrees, MS, MBA, PhD, physician, MD. And I hope that you'll see the impact that that's had through this development process. It's one of our major lessons learned, so that's why I'm coming back to that. All right, so that's a brief overview of who we are at the University of Minnesota, and I'm going to turn it over to Steve to talk about the motivation for this project.
Hey everyone, so my name is Steve Richardson. I'm an anesthesiologist, and we can talk about how we went from this time frame here to where we are today, and having this device kind of go around the world. We had a call come out early in the month of March for clinicians to think about how they could contribute from the medical school to this emerging pandemic. And as an anesthesiologist, primarily in the operating room, a lot of the things were around testing. And we were kind of thinking about some ICU capacity things, but mostly we were thinking, all right, well, we're going to have enough resources to treat these people. And then it kind of became apparent, wow, we're maybe are going to have problems with ventilator capacity. And I was reading an article through the library access on Friday night at 11 o'clock, because that's what happens to you after you spend a million years in school, is you forget what normal life is like and do things like that. And I thought, there was an article about innovation, and started thinking about this and thought, could we make an ambu bag smasher, basically? And so, here we are on the 13th, and, I started bringing this home was a 30-something-year-old triathlete that came into the university, one of our first COVID patients in the hospital. And within a few hours of being in the hospital, he was already on a lung bypass machine or on VV ECMO. And I can remember the perfusionist, I was doing a cardiac case, the perfusionist came back into the OR and it had this look of like, I cannot believe that this just came all the way across the world into our hospital. and I just put this person on ECMO, and kind of there's just a sense of fear, and he was so flustered, ran over a foot with a bypass machine and broke her toe. And that was just kind of the feeling, was this overwhelming, what is this thing going to be when it really gets here? And to see a 30-year-old have to go on to ECMO really brought home, wow, we could be in trouble here. And so the projection was early on in our institution that it could be as little as 3 weeks before we outstripped our supply. Fortunately, we didn't get there, but that was really kind of the fear. You could see, wow, this could really be a tremendously big problem in a really quick time frame. And we just did not have enough emergency ventilators in the country, only 9,000, which was projected to be enough only for Texas at that time. So what do we do with ventilation? Now, when I ask residents this in the operating room who've had 6 years of training, sometimes their eyes glaze over. So this is an enormously complex area, but breaking it down to just some simple things. When we use a ventilator, oftentimes we're using pretty simple modes for all but the very most complex of patients. And so then simplifying it further into just kind of automated ventilation, someone being on a ventilator versus hand ventilation. When we're hand ventilating someone, our goal is to pressurize the lungs, deliver a high concentration of oxygen, and allow for the removal of the expired gases, the CO2, from the patient's lungs. There's a couple pieces we can put on an ambu bag. It's something called a Peep Valve to add a little extra pressure to push that oxygen into the lungs, something that's helpful in patients who have coronavirus. But this is something that's extremely common throughout the United States. Every day, patients are moved around the hospital who are on ventilators, and for ease of transportation are put on what you would maybe see in a bag valve mask, an ambu bag, something you see in the movies all the time, see paramedics using, where you've got a bag that's attached to a valve, and almost all of them come with a mask attached. That mask detaches and can hook straight up to an endotracheal tube. In the ICU, there's an ambu bag as a backup mode of ventilation at the head of every bed in the hospital. So we use it in emergencies, during CPR, and then routinely during transportation. In the developing world, these are being used all the time right now. Someone is being hand ventilated by a medical student or a family member at this moment all over the world. Now, extended hand ventilation is kind of what we were looking at the possibility of if we run out of automated ventilators. So very sophisticated, requires a high degree of expertise to use, to set appropriately, to maintain, to troubleshoot. And we're, not only have limited capacity of machines, as you can see here, but a limited capacity of expertise. So what happens if we run out? This is real life here. This is set up not for a mock exercise here. But prior to the pandemic in Minnesota, there was a health system in town who had set up a policy in the event of whether it be some sort of chemical attack or to be a pandemic, to take a convention center and provide a family member with an ambu bag and oxygen to ventilate their family member. The advantage of this is it's very easy to do and is a quick way to add people and resources. Now, from a crew protection standpoint, this really is super resource heavy. You've got limited monitoring. You've got limited ability to protect people in those settings. So our goal looking at this was, how do we bridge the gap between this high level ventilation and having an untrained family member sit there, or a nurse or nursing assistant, a medical student, a resident, a trainee, whoever that might be, the janitor from the hospital. How do we take that person out of the loop and allow them to take better care of other people in these situations? So this is really our need. We need something that's low cost, that's scalable, that we can deliver simply to people around the world. A bridge to that capacity from companies like Medtronic, Draeger coming online. They're going to get their production capacity up and running, as they did. But as they scale up that supply chain, if we run into problems in the near term, how do we make that happen incredibly quickly, cheap, and somewhere that people not only in the United States but across the world could build something simple, utilizing an existing supply chain to make that happen. Okay. I'm going to have Aaron come back up take over for me.
So now that you've seen the need that we arrived at, I'm going to take you through an overview of how exactly we came up with a solution to bridge that gap that Steve is talking about. So Steve's talking about, we already talked about how he was up late at night at the outset of this, wondering how we could bridge the gap. So he got together immediately after this whole pandemic started with his friend Jim McGurran from MGC Diagnostics, and overnight they put together an extremely simple bag compressor prototype that you see in that top picture on March 15th. So as he said, the motivation was, how can we do this cheaply and quickly? And what Steve immediately arrived at was automated bag compression to replace this long-term hand ventilation. So while that prototype had sort of the core component, which is compressing the bag at a repeatable rate so that you can remove any of the operator error, it also had several issues. So there was an underpowered motor, no speed control, and it didn't have actually enough compression for the bag to provide enough volume of air to patients. So immediately after running into this problem, what's the next step was to come to the Medical Devices Center and see what engineering resources we could provide. So what's interesting about this is that Steve actually noticed the Medical Device Center just walking by. So that's one of our major lessons, but we'll get to that in a minute. So based off of this first prototype, Steve performed a study on a mannequin simulator at the University Sim Center, and immediately came to the conclusions that I mentioned, that there wasn't enough power, not enough compression. So the next step was to actually scale this up to improve the prototype to the point that we could do a very simple animal study, which you see 3 days later on March 18th. So after coming to the Medical Devices Center, we provided some parts and some engineering, and we put together that second very rough prototype that you see there. And with that study, we were actually able to achieve some very basic stable ventilation over a short period of time, but still had issues. So the motor was still underpowered, still no speed control, and the mechanism was very sloppy. So moving very quickly, turning over another prototype in 2 days, we arrived at March 20th, which you see there as the second successful animal study. So we improved the motor function, we added the speed control, and we improved the compression. We were actually able to achieve stable ventilation over a longer period of time, which showed us that this was a viable concept and that we could move forward with the idea of just automated compression. So then things really kicked into high gear. We built 2 more prototypes, and we arrived at another 2 animal studies, which show that we could provide reliable compression over a long period of time with just speed control, which is very important, key to this whole device. And then moving forward, this is when we engaged our clinical collaborators, and our industrial collaborators. So we got with Boston Scientific, Medtronic, United Health Group, and we handed off the project and transferred our technology and expertise to them so that they could kick up and manufacture these devices, which they did, as you could see, successfully. By May 21st, we had 3,000 of these completed, and we had an FDA emergency use authorization by April 14th. So that's a lot of information. And I'll just briefly take you through what the final device looks like and some of the characteristics that we came up with. So as Steve said, the Coventor is an electronically controlled ambu bag compressor. So it's fully automated. All you have to do is turn it on and set the speed, and you're able to stabilize a patient ventilation profile very quickly. So 3,000 of these were manufactured by Boston Scientific and purchased by United Health Group. Comes standard with a Mercury Medical CPR2 ventilator bag. The breathing circuit, as Steve mentioned, connects to an endotracheal tube, which is exactly the same as you would find on a normal ventilator. And it also includes a valve for positive end expiratory pressure, which is PEEP. So helps maintain the blood oxygenation level and helps clear out the CO2 in the blood. And it also includes a pressure relief valve for safety. So like I said, the ventilator waveform is adjusted by speed control, which means that this is a viable solution long-term for most patients that you may come across. So there are some cases where you wouldn't want to use this. So pediatrics might have some lung injury from having too high of a volume put into their lungs, and really tall people with high lung capacity may not be able to be treated long-term on this due to the fact that they need additional volume than this device can provide. But for the most part, as long as the patient is relatively normal, you can use them, or you can use the Coventor on them over a long period of time. And so this is also emergency use approved for use with COVID-19 patients. So now that we've gone through the solution, we're going to start getting into some of the lessons we learned. So the first lesson we learned is that you really need to structure this kind of innovation in an environment where you can perform high quality testing. So as I said, the way that Steve actually found the Medical Devices Center was he walked by the physical location, and he noticed that there's this unique location in the university that didn't seem like anything else, and stuck in his mind, and he came back to us later on. And actually, when Dr. Erdman first started the center, the location was a key component of his, something that he really thought would be important for the success of the center. So we're also located within a 2-minute walk of two of the university animal services centers. So the Advanced Preclinical Imaging Center and Experimental Surgical Services, who you can actually meet both of them at the Innovation Zone throughout this week, are able to provide that high quality animal testing that we use throughout this process. And those guys have extremely knowledgeable technicians that we actually worked with to collaborate and to better improve this device as well as other devices over the years. So we have that relationship built up. We're within a very short walk of those guys, and having the ability to just go down and discuss and go back up to the lab and pick up whatever prototype or whatever piece of equipment that you need, and then go back down within the same study was absolutely vital. So just to review, this allowed us to do those 4 animal tests that I talked about with 5 different prototypes in 2 weeks, which is a very fast turnaround and was extremely important for showing the FDA that we had a device that could maintain stable ventilation over a long period of time. And then additionally, we were able to set up long-term reliability studies within the Medical Devices Center. So we really were able to get all of our data all in-house, which was probably, I would say, the most important reason that we were able to get that emergency use authorization. So moving on to lesson 2, this may seem a little obvious, but you want to build a team that's well-trained in innovation. So from top to bottom, we practice innovation no matter who comes in the center. And I think that this was most demonstrated when we needed some help assembling our prototypes. We ended up with a final version of, of the alpha prototype, and we needed help assembling them within days. So we put out the call to all of our former undergraduate interns, and we got over 70 volunteers. We ended up only needing about 15, 20, but every one of those volunteers was able to slot in and help immediately because they were well trained and because we had given them the background and the foreknowledge to help us out. And then the other thing I'll mention is that having innovative physicians like Steve and like some of the other physicians that we worked with through this process was extremely important, because being able to convince other clinicians is best done by other clinicians, which again may seem obvious, but as an engineer, I was not able to speak the language. I was not able to present the data in the same way that Steve was, or in the same way that some of our other team members were. So in addition, we also relied heavily on some of our early stage collaborators to provide us with engineering help. So whether that was the motor company that we worked with, Technic, or we worked very closely with Proto Labs over the course of this to provide us with very rapid prototypes for some of the technologies and capabilities that we didn't have in the center. or whether it was with DigiKey working with our power supply and making sure that we could set up our wire harness and figure out whether or not we would have any issues with EM interference. Being able to bring in the unique skills of your collaborators is a lesson that I really took to heart and something that I will for sure be focusing on for the rest of my career. So with that, I'll let Steve talk through the last few lessons that we have, and then we'll take some questions from you after that.
All right, so embracing media. And I want to preface this with one of our pediatric surgeons likes to say, if you get in trouble in the middle of the night, load the boat. And so early on in this process, that was my goal, is to get people that were smarter than me to do things, one that I could do, but they could do better than me, and things that I couldn't do that I know that we needed. And one of the things that I wanted was to be able to tell the story of this to people, to show people what we were doing. To tell someone you've got this thing is one thing. To show them, what does it really look like? What do the people who are doing it look like? What does it look like when they do it together? That's what we brought them together for. So I called a friend who makes great commercials, and I said, I'm not sure what I'm going to need this for yet, but come and film with us, because I think that we're going to need to show people what we're doing here. Would you be able to play this video? My name's Steve Richardson. I'm a cardiac anesthesia fellow at the University of Minnesota. The reason that we're here today is that somebody needed this ventilator that we're making yesterday. Saturday night, thought I got to call my buddy Jim McGurran, who works at MGC Diagnostics. He's a biomedical engineer, and said, I think we can build a ventilator.
He had this concept, and we had parts on hand. I was able to get a hold of my team on a Sunday, iterated on the phone, and within a few hours, we were able to put together our first prototype. We're trying to make it really simple, straightforward. Off-the-shelf components were available, and also make something to help these patients.
Because of its ease and simplicity and cost, we believe that this could be easily scaled in many, many different designs.
When you're seeing a news conference and you have the CEOs of Walmart, of Target, of Walgreens up there working together, let's leverage all the resources that we have in this country between these great companies and great public institutions to make it go.
With this third version today, we're about there. We're rapidly working towards solving an emergency situation.
We need to figure out how we can scale up to bring this product and this design to as many patients as possible.
This allows those patients who would otherwise not have an opportunity to survive. It gives people a chance. And that's what this is all about, making this happen as fast as possible, pushing it to people everywhere. So after this video came out, we raised a little over $300,000 and had about 600 companies sign up to help us with this project. It was just a tremendous outpouring of support that people could see. This can work, right? This can happen. You see that, we're in the lab here, and I some of this footage in there, I left the lab thinking, okay, if I had to put one of my kids on this, I could do it, and to be able to share that with people was tremendously important in helping to build that support and bring those people on with us to keep that momentum going forward, and to share this with lawmakers, people in the regulatory space that we would need, to get on the boat with us. It was incredibly important. And then it takes us to bringing our collaborators in. This was a really dynamic situation in dealing with the pandemic, prioritizing when are we going to when are we going to stop this design? When are we going to go to, like, what if this happens tomorrow? Are we going to just build it ourselves in the MDC? Are we going to have students build this? Are we going to ask manufacturers to come in? Because we didn't, it was really a moving target. We didn't know how long is it going to be till we run out of ventilators? Are we going to run out of ventilators? And at what point, if we do, we have to freeze a design. So I, of course, as a clinician, was having a crash course in medical device design, regulation, manufacturing, sourcing, how are we going to get all the ancillary equipment that goes along with these things? So thinking about who is this team going to be? And Jim McGurran really early was very good in just getting a list so that by day 2 of this project, I made early calls to DigiKey and Technic and got them on as partners to be able to, and then Proto Labs to be able to start working and refining that prototype so that as we kind of went to the next stage, and then we're able to get our animal testing together. And then Jim was also big in telling me, look, this is going to be a regulatory problem. And I just did not want to hear that early on. I was just thinking, I don't really care. I just need something that I know that will work. And for me in my hospital, we could, as clinicians, we can make that happen. But if we're going to get other companies on board to be able to build this, that was a necessary step. And so we then, through that conversation, brought in a law firm of Hogan Lovells through the university to start working on the regulatory pieces and kind of timing these as they went along to say, all right, what is the next step going to be, and when do we bring that next group of people in? Had we approached Boston Scientific on day 2 with, just a thing in a red toolbox that we'd never tested on anything before, that was probably going to be a little bit too early. But once we had tested it and proven that, hey, we can use this thing for 8 hours, and now we're already on our 4th prototype, look at these blood gases, this is totally viable, we've got the supply chain down for this, we just need the help to scale it, now that was the right time. And utilizing the university's technology commercialization office, we were able to have, through them, reach out to Boston Scientific, Medtronic, United Health Group, who all came in and sat with us and said, okay, yeah, we can offer, this expertise here and help out. Boston Scientific said, we can manufacture. United Health Group said, we'll pay for it. And, then we were off to the races with all the key players. And the final lesson here is, being tactful in whose toes you step on. During this process, I had to threaten to quit my job because here I was as just a fellow, kind of almost a nobody in the medical system, and people were kind of feeling like, who are you, and what are you doing here, and why do you think that you could do this? Why are you doing this? And we have a quote up here. One day, very early on in this process, we needed support, and I was having trouble getting some of that support from people that didn't understand this, and was walking and trying to talk to a senior administrator, and one of the janitors, his wife's best friend had just knew someone that had COVID, and he said, I'm not supposed to do this, but I think this door might be unlocked over here, and unlocked a door for me, and got me an audience with a key player who said, hey, I heard what you're doing. I saw this, and this is who we are, and this is what we do. And if it wasn't for people all along the chain, these little breaks here and there of people willing to step up and risk it for other people that they would never meet, these huge companies that stepped up and took a risk to do this, none of this would have been possible. So that's what we've got for today. Thanks everyone, and we'll take questions.
We've got time for a couple questions, so please raise your hand. I'll bring you the microphone. Questions? Here we go.
Hi. You mentioned about the animal testing, but did you do any bench testing, or did you use the existing material or existing parts, therefore you did not need to do the bench testing? Just curious about it.
Yes, so we did both animal testing and bench testing. The major bench testing we performed was long-term reliability. So we turned on the device and we let it go for, I think it was 10 days straight to show frequency analysis. So we can maintain this waveform over hours and hours and hours. So yes to both.
Other questions?
If not, I will ask one more. About the prototype, did you make it internally or did you ask those Medtronic or Boston Scientific or any other external organization?
Also both. So the first, I wouldn't say 2 versions were made entirely internally. And then we started working with external companies. So we got a lot of parts from Proto Labs for the 3rd version. And then moving beyond that, we actually started asking for donations as a result of that video. And we got donations from companies all over the US. And this was from large companies. So Tennant was one example. They do, I think, industrial vacuum cleaners, if I remember right. They gave us a bunch of sheet metal parts. We also got prototypes from, very small machine shops that just had a 3-axis CNC mill as well. So both for the prototypes we made in-house and with external help. But we did not do any prototyping with Boston Scientific before manufacturing. We had our prototyping finished by that point.
Can you share what the biggest technical hurdles were?
The biggest technical hurdle for me, I think, and we can talk about some clinical hurdles too, but the biggest technical hurdle was making this in such a way that it was just simple enough, right? So it has to be reliable, of course, it has to have all of the functions that the FDA expected for their emergency use authorization, but we really had to be careful not to add too much because anything that we added would have slowed down the process and would have added complexity when it came to the FDA. So that was the biggest technical hurdle. Maybe Steve can talk about a clinical hurdle.
Yeah, I think some of those overlapped. Anytime that we would show this device to someone, everyone would say, well, have you thought of this? And, pretty soon you ask 5 people and you're just building a brand new ventilator that's exactly the same as the one that's in the ICU or in your operating room. So for some, that was, as Aaron said, just keeping it simple because we needed to freeze a design and be able to have something that someone could manufacture and fix in a really low resource, whether that's a low resource region of, if there's 20 patients in here, somebody's got to be able to fix it, troubleshoot it, or around the world, be able to manufacture it themselves based off the design that was released, or fix it remotely without the support of biomedical engineers in a big hospital.
Well, this is a great story. So as the chair, I get to ask the last question. It's a great story. I remember when it came out, followed it. It was wonderful to get this done. Where does it go from here?
I keep telling people that even almost 2 years now, it feels like it's simultaneously in the first mile and the last mile. We never needed it in the United States, and there are applications within the United States in different environments where it could have a lot of impact. Something really simple. So there are some things that we've been working on there, but this has gone to India during the initial Delta surge. There was used in ambulances, hospitals. This has gone to Peru, Ghana. This has been used, or Uganda rather. It's been used now for training for snake bite victims. They used to have to hand ventilate people on the way to the hospital. So there was a group that reached out to use it for that. Something that's low resource and travels well. This has spurred a lot of innovation, bridging the gap in translational medicine to kind of shake out these low-hanging fruit ideas that clinicians have on the one hand, and then I think that the story of the Coventor is not yet over. How do you create a market for something that people don't know that they even need? There's foreign regulations, all those things. So it's we did it, it's done, and it's got a long way to go.
It was a great story. There were a lot of those around, whether it's the vaccine or what you guys did or whatever it is. It shows what we can do when we all pull together and work hard. So great story. Please join me in thanking Steve and Aaron and telling their part of the story. Thank you very much.